This thing. What I want to do today is just continue. I'm going to show you a much further along example of the tic-tac-toe board that has pretty much everything you need in it except for the generate move function, which I'm going to let you guys figure out. As I said, because this is your introduction to processing, I'm giving away most of the assignment just to get you through it. I'm still a little bit concerned about timing for the next assignment. The next assignment is to change generate move so that it is actually analyzing the game tree. And I haven't done the implementation myself. I realized today that it's a game tree, it's nodes and node pointers and all that sort of stuff, and I want to make sure that I can do it in processing. It's in my mind I can do it, I just want to know how hard it is, and so over the weekend I'm going to do it. And really it's just a matter of how much am I going to ask you to do in generate move. It may be that I ask you to generate the entire tic-tac-toe game tree, which is absolutely the dumbest thing that you can do. Generate the entire tic-tac-toe game tree and just play on that tree. What I'd like to get at least a little bit into is something called alpha-beta pruning, which lets you avoid generating the whole stupid tree. What I might do is just sort of compromise between those two, because tic-tac-toe is particularly easy to get at with alpha-beta pruning. So maybe I can talk about alpha-beta pruning in general, and then we can just do it on tic-tac-toe where it's fairly straightforward and less complicated than general pruning. It's very much in flux, and I'll let you know Monday where I am. Okay, let's talk about this tic-tac-toe, the dumb tic-tac-toe. I'll remind you my specifications for dumb tic-tac-toe are here, and I'll show you where I am on dumb tic-tac-toe. So the first thing that happens is we ask who goes first, and regardless of who goes first, the first player will play with an X and the second player will play with an O. So if I click on human, then I get a board but no move because it's waiting for the human to make the move. If I click somewhere, that's my X, and then the computer immediately drops an O on you. And if I click again, and I click again, and I click again, this is not a smart. It's not even as smart as the one I'm asking you to do. This guy is simply looking at the available slots and randomly placing his piece. So if let me try to win here. So if I put that guy there and put that guy there, right? He should have gone here, but he didn't, because he just randomly picked an empty slot. And then I can go there, and it's going to keep playing. So you can also see that I don't have check win implemented or anything like that. Okay, let's talk about some of the technical details of this thing. Look at my draw. My draw is actually a big two-branch if statement. If the gameplay is on, in other words, if gameplay is true, then I'm just going to play the game. I'm going to draw the board, and then I have these two conditions to decide how to generate the move. And if the gameplay is false, then I have this other function called player one, and you can imagine what that is. That's asking the user who's player one. So let's talk a little bit about that. I've got these booleans up here, and probably should be setting those in setup, but whatever. Okay, so I start off with play game equal to false. So that means you're going to skip the first part of this branch and do the second part of the branch, which is figure out who's the first player. And then this function, once it runs, it will set play game to true, and then you're up here forever after. The other boolean is human first, and you only need one boolean, human first true, and the player one function is responsible for setting that as well. So if you choose human first, then human first will be true. If you choose computer first, then human first will be false. And then there's one more Boolean, and that's turn X. Is it turn X or is it not turn X? And that guy alternates with every move. If the human makes a move, turn X equals not turn X. If the computer makes a move, turn X equals not turn X. It just alternates. Yeah? Okay. Let's look briefly at player one. So player one is pretty straightforward, and it's using the default text. If you read the processing reference documentation, there's a lot of fancy stuff that you can do with text, and you can generate different fonts and generate font files and switch between fonts and all that sort of stuff. But it does have a default font that you can change the size of, and I would encourage you to just stick with that unless you want to get really into it. So what I'm doing here is I'm drawing a window, and I'm setting the text size to a fairly large value, 32, and then I put the text, who goes first, and that the coordinates there, 1060, say start this text 10 pixels from the left edge and 60 pixels down from the top. Start this text. So placing text can be a little bit annoying, can be a little bit trial and error. Again, processing has built-in text placement algorithms where you can center text relative to other geometric objects. But I'm not doing that. I'm just eyeballing it, right? Because this is just a one-time screen. I'm going to eyeball it. I'm never going to change the size of the screen, so I don't care about relative placement. These are all absolute placements. So I put who goes first at 1060, and that was trial and error. And if I run this thing, you can see where it is. So that's 10 from the left and 60 pixels down from the top. Who goes first? Okay, the next element of this player one function is two rectangles. And I just sketched it out on some scrap paper about what the dimensions of these rectangles were. They're centered vertically. So these guys are centered vertically. So this is the midline of the vertical extent of the window. And then this is 1/3 of the total length. So this is a square that's 1/3 of the total x distance. And so what's left is 1/3 of the x distance that's distributed here, here, and here. So this is 1/12 of the x distance. This is 1/6 of the x distance and 1/12 of the x distance. You just sit down, sketch it out, do the formulas. And these are relatively placed. So this vertical distance again is 1/3 of the vertical distance, and this is 1/3, this is 1/3. So if I change this thing to a non-rectangular shape, those buttons would be non-rectangular, but again, we're not going to do that. So I have these two regions that I would like to identify mouse clicks in. So I draw the rectangles, I change the fill and the text size to put human and computer in there. Text is weird. Text color is set by the fill, not by the stroke. So just note that. In fact, I don't know, does fill, have you messed around with that, Evan? Does fill have a stroke? Like, can you have a stroke and a fill on text?
I'm not sure.
For particularly heavy text? Can you? Okay. So that may be why, and maybe the default stroke for, I don't know. You can play around with it. So all player one does is draw this screen, and it's drawing it over and over and over again as long as gameplay is false, or play game is false. It's just drawing it over and over and over again. So if we go up here and we look at the draw function, we're just stuck down here in the else part of this thing until the user makes a selection. Now, the user selection actually doesn't occur in the player one function. It occurs in the mouse clicked section. So let's go look at mouse clicked. So mouse clicked has the same duality or dualism. It's looking at the play game thing, because mouse clicked does different things depending on whether you're picking player one or you're playing the game. And so just like draw has these two big branches for whether I'm picking the player or playing the game, so too does mouse clicked. The top part of this if statement is for the regular gameplay where you're choosing where to put your piece, and the bottom part is detecting where the click occurred relative to the human box and the computer box. And unlike the nice logic that Evan provided for us last time, this is not as nice. This is just simply figuring out whether the mouse click is inside the human box or the computer box, and that's checking. Is the x coordinate between the x bounds and the y coordinate between the y bounds for the human box? If so, human first is true, and then I just have a little debug message that lets me know that human was selected.
That's not throughout the game either. You click outside either box.
Yeah, good point. So I should move that inside. Yeah, it has to be in there. Thank you. Okay. And yeah, that's still working. Good.
It's not in one computer.
Oh, I thought it was. Got it. What am I doing here?
I know, well, the sleep button barely works, which makes it hard to silence it when you get a call like that.
Okay. So now if I click out here, yes, it's all good. And we're good there. Thank you. All right. So this is one of several billion different approaches to getting this done. So you check where the mouse is, you set play game equal to true, and then forever after you're living up here for mouse clicks. Okay. That sets human first to true or false, depending, and play game to true. So now we're up in this part of the logic. So to play this game, you're always drawing the board underneath. So there's no question about whether you're going to draw the board. The tricky thing, or not really tricky, but the thing you have to keep careful watch on is the fact that player one is always X, whether player one is the computer or the human. So you do have to make sure that you're accounting for that. So if you look at my logic there, if it's not human first and it's turn X, then that's a computer move, right? If it is human first and it's not turn X, then that's a computer move. But notice that the arguments are different. For me, 1 indicates X and 2 indicates O. And so it's really just me telling the generate move function what value to put into whatever slot it selects as its move. Again, there's a billion different ways to handle this. That's the way I decided to handle it. If either of those conditions is false, so let's say it's human first and turn X, then what's happening in the draw command? It's just waiting for a mouse click. Over and over and over, waiting for a mouse click. So let's talk about that part of the game where it's the human's turn. Okay, so here's the clever stuff that we used last time to figure out where we click the mouse, cell X, cell Y. And if it's turn X, then that means I'm placing an X, which for me is a 1. And if it's not turn X, then I'm placing a 2, which is an O. And then my draw board function is smart enough to know that a 1 is an X and a 2 is an O. In fact, I don't think we got as far as the draw board thing last time. We were getting, well, we did a little bit, but here's my draw X function, which is using the translate and the scale stuff, and my draw O, which is again using translate and scale to draw an O, and my O is just a circular ellipse. Where's my draw board? There's my draw board. Draw board just goes through the moves array. If it sees a 1, it draws an X at the appropriate location. If it sees a 2, it draws a Y at the appropriate, an O at the appropriate location, and otherwise it doesn't do anything. So that's the human side of it. Let's look at generate move, and we're pretty close to having a complete program here. I'm going to go down here and I'm going to let me do my stupid, well, I have dumb and dumber. Let's look at dumb first. No, this is dumber, I think. I don't know. They could equally be dumb and dumber. So dumb number 1, generate move, goes through the move array and just looks for an empty slot. And the first time it finds an empty slot, it puts its mark in that slot. It alternates the turn and it returns. And putting the return statement there just ends the function right there. So it will not continue to look at the move array. So this one is predictable in its behavior. So if I click human, and if I put an X here, the O is going to be here. And if I put an X here, then the O will be here, and so on. Okay. Totally predictable. You can value that as you will. One of the reasons I'm showing you this is this is, there are two aspects to writing this program. There's the user interface and getting it functioning correctly and alternating turns and so on. And then there's generating the move. And generating the move is going to be hard next week. But right now, we're not interested in generating good moves. We're just interested in generating a move so that we can see that the gameplay is proceeding the way the user interface, the way it should. So this next one makes it a little more unpredictable. It uses random. So it's going to generate random coordinates, ij, between 0 and 2. And if it happens to land on an empty slot, then it's going to break and mark that spot, alternate the turn, and move on. You might be worried that this would run indefinitely, but I guarantee you that eventually it will land on an empty slot. It's not the most efficient way to do it.
Well,
but
without a win condition, it will run indefinitely.
I just mean you might be worried that that while loop would run forever. Yeah.
Will this randomly select the same integers every time, kind of like when we were using
so processing uses the exact reverse philosophy for generating random numbers that C and C++ do. So C and C++, if you don't use a seed, then the same sequence will be generated between independent runs of your program. Processing behind the scenes is secretly, I don't know, time seeding or doing some other kind of, getting some kind of entropy into your seed, and you're getting different sequences with independent runs. And that's generally what people want. But if you're testing an algorithm, sometimes it's desirable to have it run through the same sequence of random numbers. So then you can use the seed to start it at the same place every time. So you would set the seed to 0 and you get the same sequence every time. Exact opposite philosophy. And I don't know if that's inherited from Java or not. Does anybody know Java's random stuff?
I think it is.
That's inherited from Java?
Yeah.
So the Java people decided that they didn't want to risk people not knowing about random seeds, and they figured we'll just generate random sequences every time, not the same sequence. And the C people figured, well, they should know what they're doing. And in a way, that's a design decision. It's where do you get the entropy for the seed, right? And so C and C++, I guess they decided that finding that entropy, getting that random seed, was not worth the effort. Let the user figure out where to find the entropy. Let the programmer find the entropy for the seed. And I'm not going to deal with it. So here you have to sort of trust, what's Java using for entropy to seed the random sequence? I don't know what it's using. Probably a quick Google search would tell us, but
it's probably not the time though, because using the time as a seed is not cryptographically secure.
Absolutely right.
Looks at your sequence of random numbers and knows approximately when your program started and can figure out exactly what you seeded it with and predict the next
Absolutely.
numbers in the sequence.
Yeah.
Also, I'm sure, when I'm testing my sort algorithms and stuff, right, if you run it in the same second, it pops up in the same sequence of random numbers.
Yep.
Any desirables.
Yeah.
You hit your
Doesn't say where it's getting the seed.
pseudo-random generated bits.
Just assuming it's magic.
Running the
I don't know. I'd be surprised if they were using anything other than time seeding.
You use milliseconds instead of seconds.
There are also lots of other sources of entropy on a standard computer, like network usage, the user input, the
Dev random, for example.
Yeah.
So dev random is provided by the Linux kernel, and presumably there's a dev random in Windows and other places, and so then the operating system provides the entropy somehow.
Oh, sorry.
Go ahead. Yeah.
It's on that page. The default state is current time in milliseconds.
Okay. That's the easiest thing to do, and with the minimum amount of overhead. That actually reminds me, Ben's not here, but I don't know why Jamie speaking reminded me of Ben. But anyway, the alpha computations for the parallel sort that you guys were doing, Ben pointed out to me, there's some question about how, on the merge, right? The merge is kind of parallel, but not quite parallel. In other words, if you're using 8 processors, then the first part of the merge uses 4, and then 2, and then 1. That's not strictly speaking Amdahl's law, right? Because in that second part, it's parallel, yeah, but it's not parallel with the same number of threads. Right? The beginning part of the algorithm uses, say, 4 threads, then the next part uses 2 threads, and then the last one uses one thread. So it's not technically Amdahl's law. We're still slightly saved. It's okay to kind of think of it as an Amdahl situation because that parallel merge is the amount of parallelism that you're applying to the merge is proportional to the number of threads that you started out with. Right? Like if you have 8 threads, then it's going to be 4, 2, 1. If you have 16 threads, it's going to be 8, 4, 2, 1. Right? So the number of threads that you use to do the merge is somehow related to the number of threads that you're applying overall. So it's sort of fuzzy. So if you're getting weirdness in your alpha calculations, that's another possibility. The big problem is you don't know whether your 8 threads landed on 8 cores. And Josh actually, he's not here right now, but Josh actually pointed out, some of these cores have what's called hyper-threading technology. So some of these single cores can act like multiple cores. And so dumping, say, 2 threads onto a single core may not be as bad as it sounds, because it's going to take advantage of hyper-threading, and it's going to look like 2 cores. Yes?
I think real processors are actually 4 cores hyper-threaded up to 8 cores.
Okay.
I think that's
a possibility. Okay, so all of this goes to show you that we could spend a semester or a year doing this kind of stuff. It's very technical, it's very detailed, it requires really good knowledge of the operating system, the scheduler, and the hardware that you're using to get really accurate numbers. And you look at the journal articles and parallel algorithms, and people are beating each other up over these issues all the time. Right? Timing parallel algorithms is extremely controversial. And there are best practices out there, but it changes depending on the kind of hardware that you're working on. And so one of the most common ways to get shot down if you're publishing a parallel algorithm and you're publishing timings is somebody's going to come back and say, yeah, but you ran it on this and you can't do that, and there's a vectorized buffer here and you can't do that, and it's a real quagmire. You have to really know what you're doing to publish parallel timings. So we had a first cut at it. We had a week to think about it. I just really want to emphasize that there's so much more to that topic than we did. All right, back to our gameplay here. So there's my random generate move. Now what's missing from this thing is check win. Check win is not so bad, and logically where does check win belong? If you go up into the main loop and think about the gameplay, where do you put check win?
Right before you generate.
So you can put it at the beginning or the end. You can be really smart about it, and the tiny little tweaks that you can do depending on the game that you're playing. There's no reason to check win with 1 move or 2 moves, right? So you could put a little if statement that prevents you from checking win for 1 move or 2 moves. On the other hand, this game is so simple and so cheap to check. Why bother, right? Just check win after at the end of each move, right? So generate move, maybe right at the end of generate move, you could check win, or maybe right after generate move, or there are a lot of different places you can put it, but you should check move. You should check win after each move, is what I'm saying. Okay, you don't want to get 3 X's in a row and then let the computer play and then say, oh, X is 1, right? As soon as those 3 X's are placed, you want to prevent the next move, check win. Remember that tic-tac-toe has 3 end states. X wins, X loses, and draw. So your check win function needs to accommodate those 3 end states. You can decide how you want to indicate or report a win, but if you just want to overlay text, whatever. Yeah.
Should we draw when the board is full and no one's won, or when it's impossible or like at the point where it's impossible for anyone to win?
Let it go to the end, I guess, for the draw. I'm trying to think of how hard that is. It's really easy when you have the full game tree, to do what you're talking about, but I haven't done it, so I don't know how hard it is. So let's just let you, I'll let you play to the end. So when the number of moves is 9 and there's not a win, you can call that a draw. I hope that I've given you enough here, and I can post this if you want in the examples directory. Maybe I will do that. Post it in the examples directory so that you can look it over. Your work is largely going to be in the generate move and I guess check win. I haven't done check win either. But I assume you can do check win. We can talk a little bit about generate move. How do you think generate move's going to go?
Double.
Smarter than these, dumber than game tree.
Just check for. Well, can you go through and toggle, do a check win? No, that's not good. Is it? You just go through all the rows in order and then all the columns in order, and does it see if there's one that has 2 of one thing and none of the other?
Yeah, I think that's really the only way to go. Yeah.
I was thinking you could, if you assign the values that you're using to assign to the grid spaces are like +1 and -1 points for each player, then you can check each row within some of the row. And
yeah, that's a good idea.
Easily whether someone can win the whole.
Right. So if I have exactly,
Yeah.
if I'm let's say I'm human first. So humans x's, and we call the x's 1 and the o's is -1. Then computer goes and looks for rows, column, or diagonal sums of 2, right? And if it sees them, then it's going to block. It's determined to block. Of course, it wants to check for -2 first, I guess, right? Because it wants to win first and then block second. Yeah, so that's a good way. So use different values. Don't use 1 and 2. Use +or -1 for x and o. Okay. Yeah, so that makes life a little bit easier, I suppose. What about a win then? So then you're just looking for 3 and -3? Yeah, so that's not so bad. Not as bad as I thought. Okay. So I'm going to leave this for now, and I'm going to move on to the game tree stuff. If you have questions, shoot me an email. If there's something that I've forgotten to discuss, I'll send it out. I'll send out a reply to the whole group. Okay, so we want to move on and talk about just basic game trees here. In fact, I'll make sure I put this in the examples directory. So I've assigned a reading here, Gashard's chapter 6. And he starts off with a really simple game, one that maybe some of you have seen before. Let me blow this up a little bit. So read through that. Okay. So you start out with the 5 stones, and it's player A is the first player. So player A has 3 options. Right? The player A can pick up 1, 2, or 3 stones. If player A picks up 1 stone, then there are 4 left for B. If he picks up 2 stones, there are 3 left for B and 2 left for B. So there are 3 possible moves that player A can make. So let's pretend that player A picks up 1 stone. So now you're at the 4B child. Player B has 3 options. right? Player B can pick up 1, 2, or 3 stones. Remember that the goal here is to not be the last person to pick up a stone. Yeah?
I was thinking, what does mere concurrency plus 1?
Yeah, this is a very simple game. Yeah. So, and you can see that if you look at the leaves of this tree. So every one of these guys has a 1A. So B can drive you towards a 1A at every step, right? And if I can get you to a 1A, then you're done. Okay. Where was I? Okay, so this is not an interesting game by any stretch. But most interesting games have game trees that you can't put on a piece of paper. So we start out by looking at this simple game, and then we generalize some of the ideas here. Okay. So you see how the tree works. Player A picks up 1 stone, that puts you into 4B. Player B picks up 2 stones, that puts you into 2A. Player A picks up 1 stone, that puts you into 1B, and B loses. Right? Okay. So B is a dumbass. And in fact, the way to read this thing is really at the leaves. 0B is a loss for B, 0A is a loss for A. Right?
Isn't that the way? Wait, yeah. Because A is now on
Sorry.
the move with 0 left.
Yes. 0B is a loss for A, 0A is a loss for B. Because there are no stones left, and 0A means that was B's turn that left the game in that state. So that's a loss for B. Sorry. All right. The way that these players should choose the next level is player A should try to, say, maximize his position, and player B should maximize his position at each turn. Good for A is bad for B, and vice versa. So what we'll do is we'll assign values to these nodes that kind of represent good for A or bad for A, good for B or bad for B. And there's a really easy way to do this using negative numbers. What we'll say is, say A wants to maximize his position on the next turn, and B wants to minimize his position on the next turn, and it's called the minimax algorithm. So what's good for A is maximum values, and what's good for B is minimum values. And for this game, what we can do is go ahead and assign, right, this 0B is a win for B, right? So we'll call that -1. And 0A is a win for A, so we'll call that 1. And we'll go through all the leaves here, and we'll put 1, -1 everywhere. In fact, if I have time, let me see if I can draw this down. Let me save this onto the desktop, and maybe we can just sort of sketch on top of it.
Just take a screenshot of that.
I think I can do it in my annotator. So let me go full wide here and show you what I'm talking about. Whoa. There we go. All right, let's go, I guess, do typewriter here, and we'll put -1 here. I'm going to put a frame around this too, I think. I don't want to fill, I do want a stroke. Okay, so I'll put a -1 here, and a +1 here, and a +1. Stop me if I make a mistake here.
Can you analyze this by odd and even gap as well?
You probably could, but that might not generalize to other game trees. 0b is what? -1. Sadly, that negative, when it hits that
You say sad because you can't change it.
there.
Unfortunately.
+1, and I'll just fix them at the end here. -1. Alright, so let me move all these guys a little bit. Okay, and the way this is going to work is we're going to fill in the interior nodes. And the interior nodes are going to get the maximum values of their children. So for example, this interior node 1A is going to get a -1, because that's the maximum value of its children, children. In fact, I'm going to change
The maximum value or the sum value?
the maximum. So let's go up here,
Maximum magnitude or like a.
just the maximum value. Yep.
It doesn't depend on whether it's A's turn or B's turn.
Nope. Okay, so here we take the maximum value of its children, which is -1. Here we take the maximum value of its children, which is +1. Here, +1. Here, +1. Here, +1. Here, +1. Here, oh, not yet. -1. Bless you. Here, +1. And of course, once we get a +1, we know that we can put a +1 up, right? Because, yeah. So let's just keep working here. +1, +1, +1. Put another, what's that, a -1 right there? I think I haven't missed any yet. -1, +1, and we're done. So you can kind of see why this game works the way it does. So A can choose any of its children. They're all basically equivalent. And then at every one of these, B has a -1 as a child. And so that's what B should do. B should pick the minimum. So B would go down here, and then A loses. You can see that if I can build a game tree like this, and I can do this min-max thing from the leaves up, then it's completely deterministic how to play this game. And I can do this with tic-tac-toe. X wins is +1, O wins is -1, and draw is 0. And I go from the leaves up to the root, and I'm done. Player X starts at the top and picks a 1. And then player O goes down here and picks a -1. And you just keep going +1, -1. But what happens in that situation with tic-tac-toe? It always ends with a 0.
If each player picks the move that is most advantageous.
Right. And with the min-max tree, they guaranteed. Yes.
If the game were changed that you had the option to pick 4, then A would have another strategy, right?
Yes.
Yeah. And that would be a winning strategy.
Exactly.
But how would this tree show that? Because it would be +1 like all of the other options.
Yeah, let me think about that. So it's going to be below. Let me see if I can sketch it in there. So A picks up 4, so that means I get a 1B down at the end?
No, because in that's going to be a -1, because the only possible outcome is
The A wins. The +1 is A wins.
So let me get my... do I have freehand on this? Yes, I do. So that's 1B, is that what we're checking? And then B has no choice, right? But to go down. So how do we indicate that? Just another... Let me get rid of that. Crap. I could have done all of this with... is that the eraser? Yes, good. Come on, I want a line. Yes, there we go. Nah, I'll just keep it I'll just keep it red.
I was just kidding.
Yeah. Typewriter, let's make it this is way overkill, I know, but what the hell. I'm learning how to use this, so I'm going to turn off the stroke and put, what do I want to put here, a 1B? And then I want to do another line.
Font doesn't match.
Damn it. And then a 0A.
It's almost easier writing process.
I think you're right. Okay, so what happens with 0A?
+1.
+1. I gotta be consistent, don't I? How to kill time without really trying. Okay. Hey, from my angle. Okay. +1. Yeah, that's probably a good point, yeah. Okay, what's the maximum value for child? It should be blue, yes. Okay, I'm done. And so what's the question? The question is, why is that a +1 instead of a -1?
The question is, how would A realize that that's a winning move and all the other ones are losing moves?
Right.
They're all +1.
It should be a -1.
But -1 is B wins.
Yeah. So it seems like by going through this way, we really showed mostly what B should do in any given scenario. If we took the minimum at any point, that would show us what A should do.
Unless I screwed something up with my thought
It
processes.
seems like you should alternate between taking the minimum and the max.
That's exactly right.
Yeah. Okay.
Yeah, I'm an idiot.
Only
Okay.
Someone said that at the beginning of this.
Exactly. Exactly. Like I said, this is all new to me, so you have to bear with me, but that's exactly right. So A wants to maximize and B wants to minimize. So below A, you do maxes, and below B, you do mins, essentially. I guess we could... No, I'll just do it next time.
Wait, below A you do maxes.
Yeah, because A is
But if that happens, you still get this.
But
then you alternate. Okay, so as I go from the leaves up, when
because then B takes the min in each of those, so those are all negative ones.
So
and then
exactly,
the positive one.
yes. So this is just wrong. Yeah, and we alternate. And I said it, but I didn't do it, unfortunately, because B wants to take minimums and A wants to take maximums, and so you have to provide those to B. And I didn't do that as I went up from the tree. You can see just food for thought over the weekend. This is a very idealized approach. You cannot get to the leaves of a chessboard, of a chess game. There are more chessboard states than there are protons in the universe. So you're not going to be able to do this for a chessboard. And in fact, chess, it's not known, for example, whether chess has a winning strategy. And by winning strategy, is there a formula that player 1 or player 2 can choose that will guarantee a win? That's a good thing. We don't want formulas because then the game is suddenly much less interesting. So chess is interesting because there's no winning strategy that's known. And it's not even known if there is a winning strategy, so it goes even beyond that. The suspicion with chess is that it's a draw game. If you put one of the problems with chess also is it can run indefinitely. And so what you have to do is introduce an extra rule to stop chess after a finite number of moves. And tic-tac-toe stops after a finite number of moves. But chess can go on indefinitely, and that's a fundamentally different kind of game tree. So there's a lot of stuff to deal with there. And I'll just stop there. We'll talk more about this next time. And I'll fix this tree.
Is that +1 -1 stuff in the...
It's in the text right here.
Okay.
Yeah, you can just, if you keep reading in the text, that's exactly what it talks about. So we'll talk more about it next time. Yo.
For the merge sort?